Yeah, good evening, everyone. Welcome to the October talk by the Yorkshire Centre of the Royal Meteorological Society. My name is Michael Bedu. I'm a PhD student in University of Leeds. I'll be your host for this event. We also have Ben Pickering, who is co-chairing. Ben, you want to put on your cameras just to say hi? Yeah, so Ben is a postdoc in University of Leeds, and he's here to take over the chairing in case of any issues on my end. And he's also going to highlight questions from the chat for me. And thanks. Okay, so first of all, I want to start with some logistics. The talk is going to be approximately 30 minutes, followed by 15 minutes or so for questions and comments. You can also put all your comments and questions in the chat on the right-hand side of your screen. If you check on the right hand, you see there, yeah. Just put the questions over there, and then we are going to read them out. We have the ability to display these questions on the window during the question and answer section. Now, on to the main event for tonight. Tonight, we have an interesting talk brought to us by Freya Addison. Freya, would you like to turn on your camera and say hello?
Hi.
Yeah, nice. Cool. Freya is a current PhD student at the University of Leeds. She graduated from the University of Kent in 2016 in astrophysics, but a summer internship flying with the UK atmospheric research aircraft brought her interest down to the Earth to settle with the sky. From clouds to insects, Freya enjoys studying the mist from the lens of different instruments, including ground-based weather radar. Freya was on the first official field campaign of the Biodar project, and she will be discussing how we can measure insects on a larger scale using weather radar. That's very interesting. So if you are ready, shall we go?
Yeah, we can begin. So if everyone can see my slides. So my name is Freya. I'm currently a PhD student. Last year, I took 6.5 months break during the pandemic to work full-time on the Biodar project, and I'll be talking to you about what the Biodar project is, what work we do, and what I did during my time there. Normally I talk about both radar and meteorology, but today we are focusing on aeroecology. So radar, we're looking at ground-based weather radar, and air, and ecology, insects. So we're looking at insects in the air using radar. So the outline of my talk, we're going to be going through the Biodar project, what that is, which is what funded all of this, a little bit about what radar is, and then the kind of juicy bit, animating insects, radar modeling, how we're ground truthing, things like that, and then a little bit on flying ants. So with all parts of science, we work part of a team. Our work is very collaborative. And so Biodar was conceptualized by Dr. Chris Hassel, Dr. Ryan Neely, and Dr. Liz Duncan at a Crucible event, I think around 2017. And they are the PIs of the project, so they lead the project. And then we've got postdocs, which radar scientist Marina, we've got radar and ecologist Mansi, who's just joined us. Tom is our ecologist postdoc, and then we've got 2 PhD students, myself and Will, who's just started, as well as other collaborators such as Jason and Robin. And so we're a growing team because this is a really interesting project. But what is it? Biodar is a NERC-funded grant spanning from 2017 to 2022. Insects have been observable on radar scans since the 1950s. We know that we can see biological information, but we haven't been doing anything with the data. The main aims of the Biodar project are to work out what different types of insects look like on a radar scan and how detailed can we go when classifying these targets. So how can we break it down into different groups of insects? So the project is broken up into 3 different parts. So one is simulations. We've also got ground truthing observations, and we've got our machine learning classification as well. how we can automate the process. I won't be talking about the latter, but I will. But you can ask questions on that at the end, and I'll be mainly focusing on the electromagnetic modelling and simulations. So first of all, ground-based weather radar. What is it? So radar stands for radio detection and ranging. On the slide shown on the right, there is a picture of CAMERA, which is the largest steerable meteorological radar in the world, and it's based at Sheboygan Observatory in Hampshire. We also have a collection of other radars, which are a lot smaller, and 2 of them are mobile. Radars consist of a big dish, which is the big white circle, which you can see at the center of the image, and an antenna. Through the antenna, we emit our wave packets, and then that hits something, i.e. a bee or a raindrop, and then part of that radiation is reflected back towards the dish, and that's why we need a really big dish to pick up the smaller amount of energy. This information is grouped by range, where we get a weighted sum representing the largest and most frequent targets. The Met Office have a nearly full coverage of the UK for weather observations, scanning every 5 to 10 minutes. Initially, these radars were single polarization, meaning the wave was in a single direction, but they are now dual polarized, meaning they emit both in horizontal and vertical direction. So on this slide, we can see the blue is the horizontal and the red is vertical. And what it does is basically give us more information. So we can tell the differences. So the hail, the rain and snow may look fairly similar horizontally, but when we add the vertical information, we can tell that they're different shapes. So historically, the Met Office has just labelled all biometers as clutter, which includes birds. There's well-established studies to extract birds and the rest, and now we're looking specifically at insects. One of the questions that I wanted to answer in the study was, do wings matter? So on the right, we can see a picture of a butterfly and with wings and without wings. So there's quite a difference in what we would be seeing if we were to look at these 2 objects. So we want to know exactly what we're seeing, because wings are very, very thin. So what makes a difference? So radar descriptors of insects and communities. So we get lots of different radar variables with dual polarization radar. It gives us lots of information. The main 3 that we're interested in is reflectivity. So that tells us the amount of stuff there is. So the higher the value, the more stuff there is, whether that be lots of raindrops or lots of insects. And the lower value, the less stuff there is. Differential reflectivity is the difference between the horizontal and vertical. And that tells us the aspect ratio of the target that it hits. So for hail, which is very spherical, we would expect a very low value, and we'd expect high values for elongated things such as insects, like locusts and things. Then we've got correlation coefficient, which basically tells us how diverse what we're looking at within the beam. So is it all of the same things, like a plague of locusts, where we would have a high value? Or is it a mix of lots of different insects, like a big jumble in the atmosphere, which we'd see on a summer's day in the UK? So ground truthing. So what we've got here is something called a helikite. Heli, helium, kite. So the white balloon which you see in the left image is a helium-filled balloon, and then attached to it is the red part, which is a kite, and the kite offers more lift, so we need less helium to get higher up, and also it means it can take a bigger load. And that's good, because what we do is put this helikite up to 1 kilometer in the air, and along here we have little instruments which take weather measurements, so it tells us about temperature, pressure and things like that. And then we've also got massive nets, and what we do is we put it up in the morning, first thing in the morning at sunrise, and it spends all day up there, and then just before sunset we take it down, we tie up the nets, and we collect all the insects. Now, why do we do this? It's because when we're looking at the radar, what we're seeing, and we can see insects on a clear day where there's no sort of weather events happening, we are seeing insects, but what actual insects are we seeing? And this is a way we can correlate between the different nets at the different altitudes, because there's several along in the line, what insect diversity that we have, and can we match that with the radar observations. So that's one way we could go about classifying the insects. Now, you can't do this all the time, and we couldn't do it during the pandemic. We lost 2 field seasons, unfortunately. So we also need to come up with other ways to do ground truthing. So one of them is by using simulations. So what we've got is high resolution models of insects. And what we did was there's 2 ways that we've been doing them. One is my MicroCT scanning insects. So we went down to the Natural History Museum in London. We selected insect specimens to match prevalent taxa found in the air column, so some easily recognizable morphotypes. After some experimentation, we found that insect wings are too delicate to show up on MicroCT scans. So for larger insects, we sputter-coated them with 20 nanometers of gold palladium, which allows us to map the shell of the exterior of the insect uniformly. Unfortunately, what this also does is deform the wing slightly, but we can edit that later on. The MicroCT scanning is basically a stack of X-rays, and the idea is we wanted to get mainly the outside and we didn't want to get much of the inside of the insects. The smaller insects, which were below 5 millimeter, were non-pinnable, so we soaked in a 5% iodine solution to achieve a similar effect. So the process was pinning, sputter coating, MicroCT scanning, and then we'll get an image stack. And then we move on to different things. However, with some of the larger insects, what we found, it was better to use photogrammetry, which is visible light. So what we've been doing is been pinning insects such as locusts and moths to get this nice visible photogrammetry result, which is a much cleaner thing and doesn't have any of the innards. The sequence of the events is that we took our image stack and put it into something called Slicer, which was image A, and then B and C is how we cleaned up the image using animation software Blender, and D is then when we put it into our radar simulation software. So I'm going to go through these in a little bit more detail. So we used an open source software throughout the initial process wherever we could. We used the imaging software Slicer. The CT scan initially contains way too much information, so we cut this off by thresholding, because you can see where the insect was sat on top of the foam inside the CT scanner. We pick that up, so we need to get rid of that. And also there's a lot of noise, so we just want to reduce the amount of noise that we've got, so we have a nice clear image in the end. And then we export this as an STL file. So the main part of my job was learning animation software. I used an open source software called Blender, and we used a paid for tool called ReTopoFlow to help with modeling the insect over the surface. And this took me a couple of months to learn the animation and to get to grips with all the bits. I'm still early in my knowledge, and I definitely have enjoyed learning it. I took the scan as a template, but because the insides were so full of things, and what we need for Whipple D, which is our radar simulation software, we can only have a shell. We need like a single surface. So we can't handle the amount of information that it has. So the easiest way to do that when it's full of stuff is to go over, like basically trace over the insect in 3D using the animation software, using something called RetopoFlow. So you can see in the middle image, I'm starting to draw over it in the white, and sorry, on the top right, we have kind of partway through where I've built up a shell skeleton of the insect. So I used the scan as a template and used various tools to create a surface over the top to create this empty shell. So that was the main part, and then our resultant image was the one on the bottom. Now, when we're doing this, it had some challenges. This image shows like some of the difficulties we had on figuring out the anatomy of the moth. On the left is the smooth version of the moth, and the right is the noisy version. As a non-biologist, I had many conflabs with my colleague entomologist Tom to figure out what was anatomically correct and what was essentially noise on the scan. So this included having some of the air cavities inside the insects. So we had some of the kind of respiratory system, but we didn't have a complete respiratory system because it wasn't picked up completely on the scan. So it was adjusting our expectations of what we needed. There are other things to consider as well. The amount of air really matters to the radar, but we didn't know how important it was to the model. So what we did two versions. We modeled the genital air cavity inside Bernard, which was a moth who happened to be male. And so what we had to do was I modeled kind of the air cavity around the penis and penis itself, and that was one version which we did with this air cavity. And then I did another version where we just papered over it, which we called our Victorian model, just pasting a fig leaf over it, and we compared the changes. And we also, with the Victorian model, we also did it without the air cavity inside the main thorax of the insect as well. And it turns out that we can just paper over these regions because the amount of air inside the insect compared to the rest of the stuff didn't actually have an impact on our results. But it was something that I was testing. Part of my job was to test the limits of all the pieces of software that we're using and come up with a good workflow of what we could use. So learning animation has given me a huge respect for professionals, the game industry, and filmography. One of the things I was interested in was the wings, and do they matter? Because a lot of there's been done some research before on insects and radar simulations and the Whipple D software, which I will get to in a moment. And they've just used simple ellipsoids, and they haven't bothered even putting like squares on to represent wings because they just assumed that wings don't matter. So I wanted to see whether that was a good statement, a good assumption to make, or whether it wasn't. So one of the things that we need to do was animate the wings. And this is not straightforward. What we have got here is a quite complicated, but a basic skeleton for a moth. This is then rigged with controls. We kind of create this animation skeleton, and then we weight paint, which is another process. And that's basically how much stretchiness does the model have when it's attached to each point of the joints of the wings. And then we rig that with controls. So where you've got each kind of circle, that is a joint which you can manipulate and move. And you can move them together, or you can move them independently and things like that. So from here, we can put it into different positions and thus make our moth fly. I haven't done the complete set of making Birded fly completely, but what I did do was put it into 3 different wing positions. So we had what we've got here on this display, which is our mid wing position, and then I had an up wing position and a down wing position as well. So it's a bit of a process, but it was really interesting to learn. So the main part, Whipple D. So Whipple D is a suite of software which has got a yearly license. it's very expensive, and essentially gives us the radar cross-section, so what the target would look like from a radar point of view of our targets. Historically, this has been used in the military for planes and weapons, but a few years ago was done for a bat. And so we took on the challenge of doing it for insects. So it's an extremely powerful full-wave 3D electromagnetic solver, providing fast and accurate electromagnetic simulations of material targets. What does it look like from the radar perspective, simply? So first of all, it takes the STL, which we export from Blender, from the animation software, and it turns it into its own kind of proprietary mesh. We then add our waves and what the insect is made of. And then on the right, we get the radiation pattern of for this one, it's a locust. So that's really exciting. So a single locust from the radar perspective, that's what it looks like. So let's go into a little bit more detail of the differences. So one of the first things we assessed was the resolution of the image. So in Blender, we exported different STLs which were decimated. So I think originally we had something like 60,000, 80,000, I don't know, so many thousands of plates, and the 100% full burner that we had would not run on our Whipple software. It was too many plates, too high a resolution, so we had to reduce the resolution. So we tested at this every 12.5%, and we did more in the first 12.5% as well. So image A, which is in the top left, is our 0.8% or our flatland Bernard. So you can see it's not got very many plates at all. B, we've got 1.6%. It's still a bit boxy, but it's looking a bit more like a moth. C is 6.3%. And then D is 25%, and they look pretty similar. You can see that it's slightly more boxy on the wings for C, but on D it's looking pretty smooth. And actually, what we found at 25%, there wasn't much of a difference between 25% and 87.5. There's no distinguishable differences. And we worked out that the ideal number of plates was between 20 and 30,000. So that's what we're working towards for future models, which is really good to know. We're not losing anything when we do that. And it's quicker because the 25% took 5 hours and the 87.5% took 3 days. So there's a little bit of a difference there. So another thing we looked at was different body shapes. So as I mentioned before, the previous studies that have looked at different shapes of ellipsoids and spheres for representing insects. So we did look at ellipsoids, and we compared them to our body-only moth. We compared them to our wingless moth, and a moth with a full body with the wings. Because we wanted to see how much difference it makes. So on this slide, on the left, we have an ellipsoid and we have the radiation pattern. And on the right, we have the body only, and we have a very different radiation pattern. And this is the takeaway point. Even just having the detail of a body only is a significant difference between and the radiation patterns, and thus it is important to measure at high resolution and have the detail that these insect scans give us. So one of the other things that we looked at was what the insect was made of. So we divided the insect up into parts. So on the left, we've got our locust, and we're just highlighting the wings. And on the right, we have got our moth, and we're like selecting the insect's legs. So actually what we did was we did insect's legs and antenna grouped as one. We had the body grouped as another, and we had the wings as a third group. And why did we do this? Dielectric constants. What is the thing made of? So as I mentioned before, Whipple can only handle a shell, a single shell. And so we had to fill up the body completely with one thing, but we could fill up the wings with something else, and we could fill up the legs and antenna with something else. And that's exactly what we did, because it's more representative. So for the body, we use something called borer bug goo, which is kind of what it says on the tin. It's basically ground up borer bug beetles, and it was meant to be the representation of like the chitin, blood vessels and the air and things like that. And it was meant to be a good representation of the dielectric constant of the internal parts of the insect. So we used that, and then we used chitin for the legs, antenna, and wings, because that's what they're made up of. But what we did have differences with is the density. So for the density of the legs, it was 1.15. For scaled wings, which we have for our moth, we have 1.45, and for unscaled wings, it was 1.2, which would be something for like a flying ant. So this is something that we did. So we divided up our model, which also gave a little bit more detail than you would traditionally get. Now, the other thing that we did, fourth thing, was wing positioning. So I mentioned this a little bit before. So I put it in 3 different wing positions. So one was the mid-flight position, one was the down wing position, and one was the up wing position, to see if it made a difference. And it did. So this is groundbreaking research. Before, the wings have always been ignored. The graph is a little bit hard to interpret, but there is 3 lines on the graph. The mid position is in blue, which is the outer ring. The upper position is the middle purple ring, and the black dots are the down position. And there is a difference between each of these. That means that the wing beating of the insects has an impact on what we see in the radar, which is really, really cool. And like, no one has done this before. So this is really exciting. Wings matter. Now, we just did this for a moth. I have currently just finished a flying ant, and we're going to see if it also matters for an unscaled insect. So we're looking forward to seeing that. But this is a really good start, and it just shows like having a high resolution model really matters. So what else can we do with this? Well, we can do lots with it. The sky's the limit. We can do more wing tests. We want to look at I want to look at wing beat frequency, because when I've also put in there user results and SimRadar. So what is SimRadar? So for Whipple, we are just looking at a single insect and the radar cross section for a single insect. But in the atmosphere, with our weather radar, we are looking at many, many insects. So SimRadar, we can put our Whipple product in there and simulate it for a cloud of insects, whether that be a plague of locusts or a swarm of ants, or kind of a distribution of lots of different insects. So this is what we can do next with it. We are looking at more wing testing. We're looking at other insects, and we're looking at how we can formulate these clouds, and having a diverse group of cloud representative of what it would be like in the atmosphere over the UK, and in different regions and at different altitudes. So this is something that we're moving forward with and working on. So Flying Ant Day. So I mentioned locusts, but we've also got Flying Ant Day in the UK. And this is another way to ground truth. So since we haven't been able to do field work, we have been looking at mass emergence events such as Flying Ant Day. Every year, there are mass emergencies of flying ants for nuptial flights across the UK, and these are picked up every single year and tweeted out by the Met Office on Weather Radar. And you can see on the right the tweet and kind of the blue flying ants, which are shown from the radar. So across last year and this year, we ran an online citizen science survey to map a flying ant day across the UK. We got over 2,700 responses, and we'll be using this data and 3D models of flying ants to investigate weather radar to measure this event in a more stratified way and look at the different climatic conditions that may be causing it. So on our most popular day, so the 17th of July, I believe, we have all these responses, a nice even distribution across the UK, or mainly. We didn't have as many in the north, and we don't know whether that's because we didn't get many responses from the north or whether there was just less flying ants. But this is where the radar can fill in the gap. So that was rather exciting. And then on the left, we have locations on a different day, which was the first day, which I think was the 9th of July, if I remember correctly. And it was during Wimbledon. There was lots around London, and you can see in the centre image, that's where we've got all the cluster of reports. And on the right, what we've done, we've got different size boxes. And so the boxes represent how many ants were seen. So we had like below 10, between like 10 and 30, between 30 and 60, and over 60. So the biggest boxes represent where we're seeing over 60 ants, and the two most popular responses were over 60 or between 30 and 60 ants. So what we're now doing with this data is comparing it to our weather radar. So this is a PPI scan. So this is where the radar turns in a circle at a set elevation. And this is differential reflectivity. And where you see the colors yellow and red, that's where we're seeing lots of insect activity. And so we're comparing this to what we're seeing with our citizen science survey. So this is another way to ground truth our radar. So to summarize, weather radars can observe insects. High resolution modeling is important. And future work, we're going to be looking at national scale biodiversity analysis. We are looking to see how we can classify the different insects and how we can interpret the results that we see in observations on mass emergence days compared to days when we've got lots of different insects. So we've got lots more work to do, and this is just a start of a much bigger project. Thank you very much. I hope you have enjoyed my talk, and I'll take any questions now. So I can't hear you, Michael.
Okay. Is it working?
Yeah, I can hear you now. Cool.
Yeah. Thanks so much. We have a number of questions here in the chat. The first one is from Beth. Beth is asking, will the radiation pattern depend on whether the insect is flying away from or towards the radar?
So, great question. So not necessarily directly flying towards or flying away from the radar, but depending on the angle the insect is from the radar, that will have an impact. So if it's side on, it will look quite different to whether it's like face on and things like that. So yes, it does make a difference depending which way it's facing.
Wow, thanks. We have another question from Peter, and Peter says that many insects glide if the conditions permit, rather than beat their wings all the time. Will lack of wing beat data compromise the will lack of wing beat data compromise the identification of insects concern?
Really interesting question. And I mean, the honest answer is we don't yet know. So there is, depending where you are in the atmosphere and the different altitudes, you have different representations of insects. And some insects will get up to certain altitudes and they are just following the wind. And some insects that you see in the atmosphere are spiders. So spiders have like little balloon threads, and they get themselves up into the atmosphere, and they are just passively moving along. Very small insects are not strong enough. Again, they just go by the winds, where some insects can kind of direct where exactly they want to go. So I think lower down in the atmosphere, this is our educated guess, are actively beating their wings, but some insects are not. And I think also the two question we've got, we know that scaled wings have an effect on the radiation pattern and what we're saying, but we don't know if the non-scaled things. So when you've got very small insects as well, whether they having an impact on their direction, exactly where they're going, because their wings aren't scaled, we don't know whether that's going to have an impact on the radiation pattern as well. So that's something that we're looking into, and yeah, hopefully we'll have an answer soon.
It's I find it very interesting. Insects gliding with their wings, with their wings. I feel like would the insects be able to steer their ways, especially most of the time the wind is strong. I feel like the wind can be too strong for these tiny insects to be able to control their movement.
So I just had a master student, Marta, who looked at the sort of between like the first kilometer and a half of the atmosphere, and yeah, there was directionality of insects separate from the winds. However, it is wind dependent. So when you've got very strong winds, they are unable to. And also you have less insects in flight then as well. So there is definitely wind conditions associated with it. But yeah, it's quite a complicated question that yeah, we're still investigating.
Yeah, I guess before they take off, they find a way to assess whether the wind is too strong for them to take off, just like airplanes. Yeah,
Yeah.
because I work at the airports sometime, and then because we normally give takeoff and landing conditions to pilots before they fly, and I assume the insects also have a way of assessing meteorological information before taking off. And that's interesting. All right, so we have another one from Len, and then he says that what might be the best insect to track for giving info on airflow?
Ooh. So for that, I don't know really. So in America, you've got the Mayfly emergencies, and they're quite a light insect, but they also like because of the emergencies, they have got some control. So I don't know whether that'll be the best insect. I don't really know. I'm not an entomologist, so it's not quite my field, so I don't think I can answer that. But if you tweet at me, I can get one of my entomology colleagues to answer your question for you. Or yeah, we've got at Biodar project is our Twitter. So if you look us up, we can answer the question there. So sorry about that.
Well, that's cool. We are going to leave there. We're going to make your Twitter page information available for anyone who has any. Yeah, so that's going to work. So cool. We have another question from Iswen Chen, and then yeah. Will we be able to observe the bee population changes using the radar, or is it already being done?
So yes, possibly. We don't know exactly what groupings of insects we can see. A part of my colleague's work, Marina, is looking at different clusters of different types of insects. Getting down to an individual species level, I don't think we'll ever be able to do, because there's a lot of similar species, like body shapes and things like that, and it would just be very difficult to identify. But But so yeah, individual bee populations probably not, but insect clusters, which would give us a bit more information. So you're sort of looking at similar things like bees, wasps, hoverflies, things like that. Hopefully, yes, we would be able to kind of observe and track and monitor. But no, it's not already been done. Yeah, that's why we're looking at it.
Anyway, yeah, probably maybe currently it might it might be difficult, but I'm thinking that possibly in the future that might be possible. Yes, since you're able to have a way of identifying moths and other specific insects, that's really I find very amazing. Anyway, so we have another one from Michael, and then he says that would this work help establish whether over time insects are gradually declining with regards to climate change?
Absolutely. Yeah. So one of the things that like key elements of the work is determining the biomass that we're seeing in the atmosphere, so how much insects there are, and we can already separate insects from birds, but it's being able to tell roughly like the proportion of different species and like the different clusters of morphotypes would tell us like better what sort of biomass that we are seeing, and what declines that we are seeing, and in different areas as well. So with the radars, we can look at like more specifically over different habitat types, so agricultural, forestry, towns and things like that, and we'll be able to determine like the differences. So rather than just like, the problem with insect monitoring at the moment is everything is done on a very small scale. We used to have vertical looking radars looking at insects, but we don't really have that anymore. We've got things like suction traps and light traps, which but they cover a small area. Like a light trap might be up in your back garden, and what sort of area is that covering? Looking at moths and nighttime insects. Suction traps suck a column of air, but you're looking at, maybe 30 meters air column that you're looking at. And then traditional measurements is going out and getting like 1 by 1 meter grids. So it's all a lot of assumptions that we're using. There is limits to the radar. It doesn't look very close to the ground. We're only looking at volant insects, so insects which can fly. But yes, it would be able to give us an idea of how many insects there are in the atmosphere and how that is changing over the years using radar. So.
Wow, yeah. So that's another interesting area of research that is being introduced. Very, yeah. We have one more from Beth, and then she says, "I guess you are limited by the wavelengths of the existing radars. Would a different wavelength be more optimal?"
Great question. Yeah. Yes and no. So yeah, like there's two aspects to that question. So the Metaverse radars give us like national coverage, but for insects, so normally they go up to sort of like, I don't know, 150 200 kilometers for weather. For insects, we're actually only looking at the first like 50 kilometers, just because the insects are a lot smaller. And that's sort of like the definition we get, and they're not so high up in the atmosphere and stuff. So but still, like, that regional scale is massive, and so like actually if we can do the work with that gives us a great kind of monitoring tool to be able to use across the UK at a very large scale. So that is really good. Would a different wavelength be more optimal? So we've looked at we've used different radars for different things, and maybe so the vertical looking radars I think are X band, and the Metaverse radars are C band. So yeah, you've got a smaller wavelength. And yeah, it can give us more information, like the smaller wavelengths you've got. But I think generally, with the national coverage, it doesn't, like, that weights it better. So it's not going to have as big an impact, like saying, oh no, we all need, X-band radars instead of C-band, because we can still do the research with the wavelengths that we've got, and it's much better using the technology that we have got. And yeah, across the globe, it's the two main bands are C and S. So to then say, oh, we can only do this at X band would be less impactful. So yeah.
Cool. That's really great. Thanks so much, Freya. That's been great. All the questions in the chat have been. There are a lot of other interesting comments in the chat. You can have a look at. Yeah. I think so. If you have any more questions for our speaker, feel free to contact Freya through the Twitter. She puts the link to her Twitter account in the chat. So feel free to contact her at STEM with Freya, or you can get in touch with the Yorkshire Local Centre. I will leave all the social channels details on the screen at the end as well. You will be able to rewatch this event on our YouTube channel, where it will be uploaded in the next few days. So opportunity, in case you didn't catch any part of it very well, you have the chance to watch it over and over and over again. I'm going to watch it again myself. Anyway, our next talk is going to be on November 24th at 7 p.m. as usual, where we have a talk by Professor P.S. Foster, who is from the University of Leeds. He's going to talk to us about the positive and negative impact of climate change. I'm sure you want to be there for this talk as well. So thank you once more to our speaker, Freya Addison. Thank to the Royal Met organizers behind the scenes. Thanks to Catherine. Thanks to you especially for making it for this talk. I've had an exciting time tonight because of you. So hope to see you again in our next meeting. Have a good night.